What we are going to do today is to review what we just did on Monday and go a little bit further. But then we are going to actually talk a little bit about relational algebra. And it's going to be a query language that we will use in many different parts of the class. So if you were not here on Monday, the thing that we talked most about was that there are many ways to design your database, but by far the most common one is called relational data model. And the relational data model is famous for its simplicity. And simplicity will actually make you more resourceful. You will think differently because you are trying to do things as simple as possible. In a way, this is kind of the reverse of all the other classes you take, right? So you learn more and more complicated languages, Python, all these different modules, C++, and pointers, this and that, right? And the point is that when we come to databases, we first look at simplicity and then think about what simplicity gives us. And we are going to talk about very minimal ways of doing things. And then we will talk about pros and cons. So the relational data model is very, very simple. So the idea is that you have a database which is a set of relations. Each relation is a set of tuples, which we call relation instance. That conform to some schema. So that conform to some data model or schema. And we represent the schema using attributes and domains. So the schema of a relation is attributes, and for each attribute there is a domain, the set of valid values. And one of the very simple rules is that all your domains are very simple. So only simple domains for relational data model. Things like integer, string, date, but not things like records and dictionaries and sets. Those are not allowed. Okay, very simple stuff. That's why we are saying it's very simple, because it's a flat data type. And all of these terms are actually logical terms. So you can have logical terms or physical terms. There is a distinction, and we will talk more about that. But the terms, things like a relation, is the same as a table. Very often it's the same thing. But in reality, a table is something you store in a database implementation, whereas a relation is a mathematical concept. So we talk about tuples. If you know, like mathematics, tuple is basically a multiplication of different domains drawn from that. But it's the same as basically a row in a table. And we talk about attributes. Generally, you refer to them as column. And if you want to be super, complete, the domain of an attribute is the same as the data type, right? So these are kind of the same things. Kind of get used to these terms. We will use them all over the place, okay? So the most important thing we talked about, there were two basic things. One is that a relation is a set of tuples, and that we only can have simple domains. Okay? These are the two important things to remember. This will come up over and over and over. Okay? So anything else it's kind of common sense, but remember that the relations are set of tuples, and the attributes can only take simple values. And you can represent a relation in many different ways. So the theory of databases comes from logic, for those of you who love or hate logic. So you can write it as a table. So you can have a table called heroes. Okay. So you can have what's her last name? All right, we're gonna keep it at Kara. I don't know her last name. Okay, so I have a relation between two attributes, alias and name, right? So basically, this relation called heroes associates the alias with the name of the hero, and I can represent. So this is the name of the relation. These are the two attributes or columns. Okay, and in this case, I have three tuples in this instance of heroes. So as far as my universe is concerned, there are only three heroes for this implementation. And these are the three heroes that make up my relation. Okay? So you can also represent the same thing. So this is kind of the table representation. But you can represent the same thing as logical statements. So all of you have probably seen some logic class. So you can say that there is a predicate called heroes. And in this predicate heroes, there are three facts. So one fact is that Arrow and Oliver Queen are related. So this is a fact. I'm putting things like a string, but ultimately, for the logical representation, it doesn't matter they are strings or not strings right now. But obviously, when you implement, you care that one's a string, the other one's an integer. So all of these are basically valid instances, and they are facts about the world. And my schema is that I have heroes, alias, and name. Okay? So this is my schema. And this is what is true about the world. So this is the schema. Okay? So as far as I care, these are two same representations. Why this is important is that because if I were to represent it like set of facts, stating the same fact twice doesn't really give me any new information. So if I were to say, if I were to add one more line here, bless you. So do I have 4 facts or 3 facts? I have 3 facts. One is, repeated twice for emphasis, but I really don't learn anything new. So this is why we say it's a set, because ultimately what I care are the unique facts. Okay? These two are the same relation because that's what I know. This is the information that I have. And the third way you can think about this is actually a set. Since I keep telling you it's a set, so you can write something like heroes is actually a set with tuples like Arrow. And you can actually have the tuples with the attribute is an alias, and Oliver Queen is the name. So you can list your 3 tuples here and represent the whole thing as a set. So they are all the same. They represent the same thing, right? When I say set, these all 3 are equivalent. So often you see different ways of representing them in different books. They're all the same. Okay? So I'm just trying to hit you in the head with the point of set. This is going to be important in a second. All right. So relations are sets. And the very important point is that relations represent some object, real or abstract, in the real world that you are trying to store information about. And given what they represent, okay, that you want to have a key for each relation. And each relations have a key by default. So we talked about what a key is. A key is a set of attributes that are unique in the sense that no 2 tuples can have the same values for the key. Okay. So there are keys can be a single attribute, multiple attributes. A relation can have more than one key. So let's go back to our example. Given hero's alias and name, what is the key? Is there a key? What attribute is unique? Is name unique? Can you have 2 flags? So the thing that we talked about was that depending on how you define your key, that tells you what the relation is storing. So I am storing, the actual superhero enterprise. So in this case, alias is unique. Is the name also unique? Which can be a key. Can the name be unique? Are there any 2 heroes that have the same regular name? I don't think so, but the problem with using this is that you probably all know way too much more about this than me. But I would say that name is also probably a key. Okay. If we were storing a different table where we stored which actor played which hero, then this would be a little different. Okay. So generally what you do is, if you have a single key, you underline that. You say that, alias is the key. You don't want to underline both alias and name because that means they are together the key. In this case, either one is fine. And so let's do this one. Here's another relation where I want to store which actor played which hero in which year. Right? So you have the alias of the hero, the name of the hero, the name of the actor, and the year for that. Right? So now think about what's a good key for this one. Yes. Okay, let's see. Would it be the actor name? Is actor name unique? Can an actor ever play 2 different heroes? Technically they can. Has that ever happened? I don't know. Okay, see, you see? Actor name and year? So, can the same actor in the same year play this two different heroes? It will be confusing, but maybe it's possible, right? Yes. Elias and year. Okay, so we didn't like that one. That didn't work. Elias and year. Is that Elias and year word? Is the same hero in the same year played by two different? They don't like that actually. The franchises don't want you to do that, right?
Well, they don't like it. I'm curious if you have like years. Is that like if you have a franchise and there's like multiple years, would that be like would that cause an issue?
All sorts of things that can cause an issue. This is why we are going to see this is a good or bad model. We are going to analyze this mathematically later on. So let's say that Elias and here is a key, so that we are hoping that franchises don't reboot on the same year. I mean they reboot way too fast, but this is happened. I came home after a trip, so we are watching our recorded shows, and I told my husband, I said, well, let's watch the DC comic ones first. I said, wow, you finally figured out the distinction between the Marvel universe and the DC universe. He was like so excited. So, if you see errors in my data, you're welcome to correct it. I am not as deep into this. But, okay, so let's say that Elias and year is 1. And so let's see. Actor name and year, we were not sure. So let's say that Elias and year are unique. Okay? So one of the questions we are going to ask is that even though this is correct probably, correct in the sense that it makes some assumption and then it may or may not work for real data. But let's say it is. We have to ask later on whether this is a good data model or not. And we are going to see this mathematically. Okay? But for now, I'm going to keep it as such. Okay? So, I'm going to put one more. Or let's say hero in movie. Okay? Which is going to have hero name or hero alias, okay? And movie name. Okay? So what's the key for this one? Can two movies have the same hero? Yeah? That's the whole point, right? Of the franchise. So movie itself is not a key, because if the movie was a key, you can only have a single couple for each movie, right? That means you cannot have multiple heroes in a movie, which is violated for which movie? There you go. All right. Can you have hero as a key? If you had hero as a key, that means you can only have one tuple for each hero, right? So that means each hero can only have one movie, which is not true, right? Okay. So my key is both attributes, right? So in fact, if you did not have any attribute that was naturally a key or any set of attributes, all the attributes in the relation by default have to be a key, right? Because you can never repeat a tuple twice, because it's a set of tuples. So by default, this is the key, but sometimes you have a subset of them that's a key. Okay? All right. So this logical representation, you can take the schema and create a table to store it in SQL. Okay? We are not going to do much SQL, but basically I'll show you the very basic syntax for doing that. So SQL basically maps one-to-one a relation to a table. And the general syntax is something like create table table name, you open a parentheses, and then you have attribute, data type. Okay. So the syntax in this case has an open parentheses and a closed parentheses. Everything in between is a list of data types. Okay. And then if you actually had additional constraints, you specify them either next to it or after here. And I'm not going to go into constraints too much, but for example, the keys are one of the basic constraints you would specify here. And there are many other types of constraints, whether something should have a value or not. Yes?
Is that after the semicolon?
No, it's just badly written. Yeah, like this. So SQL is case insensitive, and I will do my best to use the capitals for keywords that you can recognize. But you can use whatever syntax you want. The spaces are not important, but please, oh please, write things that are readable for other people. So, for example, so the data types in this case are things like int for obviously integer or anything like that. You have obviously float. Okay. But stuff gets a little bit more interesting. So you can have numeric values. Basically, this is fixed precision, not floating point precision. Very important in databases because you store information about things like money, so you don't want to lose precision. You can store strings, but there are many different ways to store strings. So you can store strings at character strings of up to a certain length, or you can have variable character strings. So this means that it will always allocate 10 characters. This means it will allocate up to 10 characters. And you have a very strong date and time and timestamp data types with lots of fun operators over them. That is one of the cool stuff about databases. Booleans. You have nchar, I think. It's been a while. For Unicode, my nemesis. We will see some others. There's binary large objects and so on, but often these are kind of the basic ones. So just to do a simple thing, let's create a very simple data type for hero actor. So I will say something like so we said, for example, there is an attribute called alias, and let's say that was a character string up to 20. I never ever use character strings unless it's something for very basic, like course prefix has to be exactly 4. For everything else, I generally use variable characters. And name. All right, are you all excited about Beflek? And the year is an integer. Okay, you can put the commas at the end or the beginning, but this is actually so much more convenient when you type. So either way is fine for what to do here. And then if you, let's say, for example, define a key, you would say something like primary key, okay? And then you say alias and here. Now there are lots of different versions of this. You can give all the constraints a name. You can say other things are unique and so on, but this for now is as much as we want to decide. Okay, and we'll get back to this, but basically, you can just map everything to a table. That's why we use the term table, even though we are not yet working on this. So, this is all I want to say about the relational data model. What we are going to do now is we are going to move on to relational algebra. And so we're going to do some relational algebra, then give a break. But let's do some of the basic relational algebra, and then we will go back. So I've spent some time to create a database that is semi-correct. I don't know what's wrong with my Firefox today. Come on. Okay. All right. So this is not necessarily a good database, but there's a real reason why I structured it like this. So we can actually play with the relational algebra. And hopefully I actually separated the Marvel and the DC universe correctly. Otherwise, you may be dying. So I had to look it up. We are going to go back to this data model. So basically, we said a database is a set of relations, right? So I have one, which is names of heroes in the Marvel universe, the names of heroes in the DC universe. This is the names of heroes in the that have a TV show, which may not be old ones, but this is what I have. And just so that it would be simple, I used an ID to map between heroes and other things. Doesn't mean that you have to use an ID, but otherwise it would take us too long to write other things. And as I was writing this, I felt really, nostalgic for the swamp thing. I don't know why. I guess he's not a superhero exactly. He protects our environment. And then I have a set of movies, right? So given a movie, you have a movie ID, the name, and the year. And I had to put some, DC movies, but, like Green Lantern's a horrible movie. So I have some TV shows, and I made a design decision that all TV shows are for a specific hero. We can talk about that, whether that is good or not. And then I have this basically one relation that stores which hero is in which movie. Okay? And in fact, for example, M6 has many heroes. So does M11. If you go back and see, those are the Avengers movies. Okay? So there are lots of little things in there that are, by design. But if you want, we can crowdsource and make this a complete database by the end of semester. So, okay, so we are going to go back to this. This is online if you want to see it. But we are going to use this to actually write some queries. So, relational algebra is a query language, but it's a mathematical query language. It basically has very simple operators, but by combining them, you can actually write increasingly complex queries. So, with the exception of one operator, almost everything you can write in databases like SQL, you can convert to relational algebra because they're all derived from these simple primitive operators. In fact, we're going to learn more operators than we need. Just some of them are for convenience, whereas you can actually derive those from the others. So the small set of operators that you absolutely must have is called the relationally complete set of operators because those you can use to derive all the others. And they're actually quite powerful. So you will find this material to be seemingly simple, but when you try to write your own queries, kind of complex. So you have to write your own queries. Okay, like everything when we learn programming, you have to do it yourself. Okay, so you have to spend time to be frustrated with it, and we'll give lots of examples. But it's important that you do write some. So relational algebra operators, think of them as input is set of relations and output is a single relation. So what that really means is that you get a set of tuples, you produce a set of tuples. So input and output are the same type. And as I said, a lot of SQL can be translated to relational algebra. And in fact, most databases implement not SQL, but takes your SQL and compiles it and runs it as relational algebra. So this is really what is under the hood in databases. And even more importantly, this is what we are going to use to talk about some of the normalization data design theory. Okay, so relational algebra operators are all Greek symbols. So I welcome you to learn LaTeX here. So let's talk about the basic idea. So we said that relations are sets of tuples. So we have a number of set operators. Okay. So you basically have union, set difference, and set intersection. Okay. So you can take two sets of tuples and you can find their union, or you can find their intersection, or you can find tuples that are in one but not the other. But to be able to do any kind of set operation, you must have two relations that have the same exact schema. Okay? So set operators are only defined for two relations that have the same schema. Okay, so if you have two relations that have the same schema, you can say something about set union, set difference, but for others you cannot. So if we go back to this, Marvel heroes and DC heroes, are they set compatible? Are they union compatible? They have the same schema? Okay. And DC heroes and TV heroes? Sure. And how about movies and TV shows? No, right? So remember that when you're writing set operations, you will always want to take from this, take from that, but you cannot do it unless you have set operations. So you have the same schema. Okay, so set union. I know this will sound like an insult because we have done this in Python, but okay, let's remember what that means. Okay, so R union S is the set of tuples in R or in S. Okay. So take all the tuples in R and S, put them in a new relation. Remember, relations are sets, so you will not repeat the same tuple twice. Okay? So if this was R and this was S, this is the set union. Set difference. R minus S. Set of tuples in R, but not in S. Okay, so it will be something like, if this is R and this is S, it is this. So what would this part be? Incidentally, set difference is one of the most important operators. Okay? You will see that this gives you a lot of new queries because it's the only one that has negation in it, that are in R but not in S. Whenever we are doing something that requires to find things that are not here, you will use some sort of set difference somewhere. Okay? And then set intersection. So for example, set intersection is not a necessary operator. If you have set union and set difference, you can get set intersection. How could you do that? Yes. Right, so you have, this is R union S. Okay. Subtract from this one, which is R minus S, and this one, which is S minus R. Okay. So R intersection S is the same as R union S minus R minus S union S minus R. Do you do this in Fox? Okay. And this is also true because you can write this logically as equivalent to the same thing. Okay. So what does that tell us? So let's write some queries. Okay. I want to find all heroes in the database. What do I do? If I want to find all heroes in the database, I want to take Marvel heroes, Union DC heroes. These are actually a subset of the others, so I don't really need to do anything, but you can figure out, what that is. So all heroes that are in both universes would be what? That I would have to take the intersection, okay? Which we know that I was told over and over by my husband that there is no such hero. So it will return you an empty set. It's a query that you will execute and find nothing. But if you want to write it logically, this would be how. Okay. So let's find all DC comic heroes that are in a TV show. Okay. And I also want to find all Marvel comic heroes that are not in a TV show. Okay. That didn't work very well. Okay. So all DC comic heroes that are in a TV show. Like if in one table you have an ID, but one is called HID, other one is called SID, they are considered different attributes, right? So they have to have the same attribute name and the same domain. Logically, we will not consider them the same schema, right? So if you had two tables that had equal number of attributes, and but they had different attribute names, they would not be considered the same schema, right? You cannot operate, this is, logically you cannot operate them, right? In implementation, in a database, they will probably cast them. So, the database will not complain, but I will. So I'm trying to do it in the pure mathematical sense. It should not be right. But technically, yes, there are all sorts of such things. Okay, so tell me, DC comic heroes that are in a TV show. Query? Okay. DC heroes intersection TV heroes. Okay. And then all Marvel heroes that are not in a TV show. Okay, so let's see. Marvel heroes minus. Well, would it work the same if I just subtracted TV heroes? Okay. So that yours would work too, right? But mine is a little simpler, right? So this is one of the things that you are going to work on. Okay? It's not going to be easy at first, but you have to simplify. So that would also be right, but this is also just fine, right? So this set contains all heroes that are in this universe, and this contains all heroes that are only in TV shows. If you subtract one from the other, then you're fine. So this set contains more things, but it doesn't matter because this is the way we think about the set subtraction, right? So this set contains other things, but I only want to subtract this part, but subtraction will work regardless. Okay, and let's write one final one. So all heroes that are not in a TV show, or that were not in a TV show. So all heroes, regardless of which universe, that were not in a TV show. Intersection or union? Union. Yes, good. Okay. Would it be the same if I wrote it like this? Would this return the same result? Okay. So is is one more efficient than the other? Well, yes, and who cares? So remember that this is a logical data model, right? So we are not going to care as much about efficiency, this is not implementation, but we are going to talk about simpler and easier way to write the same thing. But there is nothing that says necessarily that the top implementation will be actually faster than the bottom implementation. Okay? Because it really would depend if this was really stored in a database, how these are stored, right? If, let's say, this was a distributed database and Marvel and DC Heroes are in two different, places, and let's say the TV Heroes was replicated, it would be better to do the second query and then send the tuples. So, there's lots of different ways. One may be better than the other, but the thing to notice is that there are multiple ways to write the same query, okay? And this is going to be very important later on. So, let's give like a 5-10 minute break, and then we'll continue on with this.